A very good morning to one and all. I welcome you all to the day 5 Atal FTP on bio-inspired computing for data analytics. Today we have 3 sessions. The first session is on hands-on session on data analysis using Python. The next session will be optimization of biometric recognition systems. And the last session will be the validatory session. So now we have the first session. Sir is already available. A very good morning, sir.
Yeah, good morning.
Yeah, Dr. Wilford Godfrey, sir, is going to take hands-on session on data analysis using Python. Over to you, sir.
Yeah, thank you. So, good morning, everyone. So, today we'll look at some of the. We'll look at basically two algorithms. So, we'll look at the um particle swarm optimization as well as gray wolf optimization. So, so we all know about the particle swarm optimization. So basically, like here we have uh, we basically like in general, like in any optimization problem, like you have a optimization objective, right? So I'll just share my screen. Okay. So today we'll look at PSO and Gray Wolf optimization. So particle swarm optimization and Gray Wolf optimization. So now we will initially have a look at the particle swarm optimization algorithm. So basically, we have in any optimization problem, you have a objective function, and you have some constraints, right? So if you have a single objective function, then you have a single objective optimization problem. If you have multiple objective functions, then you have a multi-objective optimization problem, right? So now here, like typically, like with every algorithm. So in a brute force algorithm, so you need to find out, say in this optimization problem, you basically need to find out the value, some value of the variables for which the optimization objective is satisfied. Maybe like your optimization objective is say to minimize or maybe to maximize, right? So maximize some functions, right? So now at what values of the variables at which this objective is minimized or maximized is what you need to find out. So you get to a brute force solution by varying all possible values that the variables can take, and then like if you are able to find out the space in which like the variables vary, I mean the solutions vary, then like you have a brute force algorithm, right? So now we don't want or like we don't have that much of compute, or we don't have that much amount of time to compute the entire solution space. Rather, like we are more interested in some kind of heuristics which may give us not the optimal solution, but then like near optimal solution. So in all of the heuristics, what you do is basically like you initialize some solutions, and then you iteratively like you keep refining the solutions such that like you reach the optimal solution at the end, right? So that is what we do with respect to heuristic, right? So or near optimal solution at the end, right? So that is what is the normal flow of operation that happens, right? So similarly, like with respect to the particle swarm optimization, also we have some particles. So these particles are, or the position of the particles are maybe randomly initialized, and then the position of the particles are varied, and based on which, like by this refinement, like you arrive at some near optimal solution. So the variation depends upon a factor which is called as the inertia and cognitive and social parameters, right? So the particle's position, so the solution may be called as a particle's position. So it varies based upon the inertia, cognitive, and social parameter. So basically, the particle position at or the new position of a particle, that is given by xi k plus 1, where k plus 1 is the iteration. So this is given as the sum of its previous position plus vi k plus 1, which is the particle's velocity. So now the so it means a particle's new position is computed as the sum of its previous position plus its velocity. So the velocity of a particle, that is given as vi k plus 1, is equal to wk vki plus a cognitive term as well as a social term, right? So this you call as a inertia. You have a cognitive term and you have a social term, right? See, the cognitive term is made up of some parameters which are the cognitive and the social parameters, which are C1 and R1. So C1 and C2. So C1 into R1 are some random number. So C1 R1 PKI minus XKI. So this together becomes the cognitive parameter. Then you have a social parameter, which is C2R2 pkg minus xki, right? So now what is this pkg and pki? So this pki is the this particle's best position, and this is the best position of any particle, right? So you have a global best and this particle's best position. So that determines what the velocity of this particle should be, and based upon this velocity you refine the position of this particular particle. So now this we see as the updation rule, right? So initially, like what we do, we set the or initialize the variables, maybe then randomly initialize the particle positions and randomly initialize the particle velocities, right? Then you so these are constants. The constants are say C1, C2, and WK. This is the um, inertia weight. So now these are some of the constants, and these are these are initialized. So you have a initialization uh, step, right? So in the initialization step, like what you do is you initialize these variables, then you randomly initialize the particle positions and the velocities. Then you go on to iterate, so which is to find out the fitness function of each particle at each position, and then keep on checking, like updating for all the particle velocities and updating all the particle positions, and you keep on iterating for all particles and all maybe several number of iterations. So basically you have two more parameters, so the number of iterations, right? And now another thing that needs to be decided is the number of particles, right? So over several iterations, you update all the particles position and the velocity by every time calculating the particles fitness, right? So now here, like you can use if you have a minimization objective, then you can use your objective function itself as your fitness function, wherein like you can check for at each instance, like you check with what the value of what is the value that you get with respect to your objective function, right? So that itself may be considered as a fitness function, and then you iterate and find out the particle velocities and particle positions, and you iterate over several iterations, right? So now now we see that like there are three things. One is the inertia weight, and then you have two constants, social and cognitive constants. So now they sort of dictate like how um, the particle is also going to move, right? So how it is going to move over the space in order to reach your objective, right? So now we will try to see like how this is overall implemented. So so I'll is there a way to send a message? Yeah. Hello. How do I send a message? If I want to share the link for the Google Colab, how do I do that?
Sir, we can copy the link in chat box, but the owner of the team has disabled this chat box. So only the organizer can enable the
Sir,
chat box.
uh, sir, you can forward it to Lavanya ma'am, sir. Ma'am will post.
Okay. So I've shared the links. So here, we'll go through this code. So I mean, all the codes that I've taken from the internet only. So I have given the links of all the codes at the top, so you can check them as well. So here, what we see here is that um, we have a cost function that is given by func1. So you basically have a function like which you need to optimize basically, or you basically the optimality is given by, it's a minimization objective. So the value of x of 0 and x of 1, for which this total is minimum, right? So so what will be, say if you have um, if you have say x comma y, or like you can have x of 0 and x of 1. What is the value of x of 0 and x of 1, for which x0 square plus x1 square is minimum? What is the value of x of 0 comma x of 1, for which, so what is the solution here? Hello, what is the value of x of 0 and x of 1, for which x of 0 square plus x of 1 square is minimum? Hello, hello. Okay, so we will. So here, like that is the function that is given. Basically, like you have the objective function given there. So So you're in receipt of the links. Okay. So basically, like here we have the cost function that is defined over here, and then like we have a particle. So a particle, every particle has a position, it has a velocity, it has a best individual position and best error and individual error, right? So at any moment in time. So then like we also have two things. One is the velocity and the position, right? So we have all these variables with respect to every particle. Then a particle may also check like we recur to every instance we need to check the fitness, right? So the fitness is basically is what is given by this value, that is the error best and error I, right? So now we in order to evaluate the fitness we have this function which is the evaluate. Then we have after checking the fitness, then we require to update the velocity. So in order to update the velocity, as I already told you, like velocity function is a function of three variables. So basically it consists of w, then it consists of cognitive constant, I mean a cognitive term, and then it also consists of a social term, right? So together, like you have these three terms, right? So you have the first term, which is the inertial term, then you have the cognitive term, and the social term, right? So here, like using these constants, these are constant values. So based on these constants, you compute these three values, and then you compute the position. So first of all, you compute the velocity, then you compute the position, right? So the position is basically given by these functions, right? So now every time whenever you check the position, like you also see like if you are going out of bounds. So basically like you are going to have a solution space that is given by, say, in the x-axis something like -10 to 10, and in the y-axis maybe -10 to 10, right? So your entire solution space is going to be here only, right? So within this solution space you need to find out what is that particular value of the variable which is going to, what is that x of 0 and x of 1 that is going to give us x of 0 square plus x of 1, x1 square, to be minimum, right? So you need to find out this, right? So it means that and moreover, like the variables x of 0 and x of 1 can be these are continuous variables, right? So x of 0 and x of 1 are continuous variables. So if they are discrete variables, then you may have something around 400 points that are to be checked, right? So when it becomes continuous variables, then you are going to have infinite number of points where these can I mean which you need to check in order to find out the minimum in a brute force kind of a scenario. So that's the reason like we go for some kind of heuristic by which like we are able to find out the solution, right? So here like so um, whenever the solution space say for instance a particle is here, now using the update, we calculate the next position of the particle as this one, so it goes out of bounds of this region. So it means that it needs to be brought back into this region, right? So you keep the bounces this particular position only, right? So that is what is done using these two if conditions. Then, so this is all about the particle. So with respect to particle, you have the various variables of the of every particle, and then, or like maybe the features of every particle. Then you have three functions. So one is the evaluate function, then you have update velocity and update position. So a particle has to be updated with respect to its velocity and position. Now in PSO, basically you have the main program. So in PSO, what you do is you um, um, you find out like your um, so here like the number of dimensions may be equal to 2. So so here in PSO, like we have the original loop, so the major loop. So in the major loop, like what we do is, this is the major loop. So what we do is, for maximum number of iteration and for every particle, what you do, I first of all evaluate the fitness, then I check like what is its position, right? So whether the what is its fitness, right? So whether the fitness of the particle is the global burst, or like if it is not global burst, then I keep updating its position, right? So then I keep updating its velocity and the position, right? So that is what I do with respect to every number of particles. So here what I do is I compute the global best and I update the global best. Then I update all the position of the particles. Then I keep repeating this for maximum number of iterations. That is what I do by this particular loop, right? So as I keep on repeating this, I finally, like after repeating it for several number of iterations, I get the final best position and the error position, right? So here, like when I run, I initialize some of the dimension of the region and so on. So initially, like I keep the particles at this position, then I bound the region to -10, 10 and -10, 10, x-axis and y-axis. Then I called it PSO function. So the total number of particles that are to be there initially are 15, and the maximum number of iterations to which the loop is going to iterate is 30. Right. So here I have the um, uh, uh, particle swarm optimization algorithm. So you can run these as it's given in the Google Colab. Like you can run this. You can run this by clicking on the left. So in the left, at every cell, like you may have a thing like this. So you may click here and you can run this sheet. So if you have any queries, like you can just ask. So any queries? We'll go ahead to the next program. So uh,
Sir, can you please share those links to Lavanya ma'am, Dr. Lavanya, so that she can post
I
it
have
in the
already
chat
I,
box?
I have already shared it. I have sent it to her email right at the beginning of this.
Okay,
As I
sir.
was showing the PNB files Yes, I shared it.
Okay, sir. Thank you, sir.
Yeah, thank you. So you have a library in Python, so which is called as the PySwarms library. So um, you can in Google Colab, like you can install the PySwarms library by using this command, and then you will be able to install in Google Colab, right? So this PySwarms is a swarm intelligence, or like it's a research extensible research toolkit for particle swarm optimization, like with various variants of this particle swarm optimization algorithm. So you can check out this library, which is the PySwarms library. So it enables basic optimization and also interaction with swarm optimization. So I request you to check out this particular library if you are interested in working in this direction. So now, in order to use PySwarm, like what you do is you import this PySwarm. Here, we have just shown uh, an optimization of a sphere function, right? So, the entire program is quite simple. So you just have the objective function that you need to optimize, then pass it to this function called as um, uh, uh, optimize, right? Optimizer.optimize. So basically, optimizer, you say that this is a single objective optimization, and you're going to so in this, like you're going to use the global best PSO, right? So it may have various variations of this particle swarm optimization, right? So you can select like any of these variations, right? So now once you select like what is the kind of optimizer that you want to use, then you can select what is the function that you want to optimize, right? So you can select and how many number of iterations that you want to have. You can select the number of particles and everything. Then you have the cost and the position after optimization that is given over here. So you have the final result in the left hand side. So now once you have the result, then you can also plot the counter, right? So you have the sphere function. So in this sphere function, like what were the initial positions of the particles that can be plotted, or at various iterations you can plot like how it moves, and also this is with respect to a contour plot, right? So contour plot means, say for instance, say for instance you have a hemispherical vessel. So if you have a top view of this vessel, then like you are going to have uh, such kind of circles, right? So that is what is going to be a contour plot. So similarly, like if you are having a sphere, and if you're going to have a top view of this sphere, then like you're going to have concentric circles like this, right? So that is the contour plot. So here, you have a contour plot that you get, and this is going to be your entire solution space, right? in this solution space, what are the initial positions of the particles that you can obtain. Then, like, you can also have a 3D plot of the entire region. So, solution space like that also you can obtain using a plot like this, right? So this is a wonderful library, like which you can try if you're interested in working in this area. Okay, I'll go ahead to the next thing. So next we look at in all these places, like the source of the program has been written over there. You can also check those sources to learn more. So this is another one interesting source, like which I found.
चाय पीने गई
So this is another source, like where we have the function. So and function visualization right over here. So here, like we have this objective function that is given by this function. So basically, like you want to find out the minimum value of this function. I mean, you need to find out the values of x and y for which this function is minimum, right? So that is what you need to find out. So what we do is, like, first of all, we do a contour plot of this function, right? And we also uh, locate the minimum point in this entire contour plot, right? The contour plot of this function along with the minimum point location is what is given by this particular x, right? So using this code, like, you will be able to do that. Then we initialize 20 number of random particles. We initialize its position and initialize its velocity with some values, and then once more, like with those 20 particles, we find once more do a contour plot and identify like where those particles are exactly located, right? So we have some of these particles, maybe some are out of bounds. So we have these 20 particles. Then we what we do is, like you try to uh, iterate, right? So you initialize like with the p burst. Then as we already saw, like you have some initial g burst. Then you have these values like c1, c2 and w, which are some constants, like and then you keep finding out the positions, right? So the new positions of the variables in every iteration for every particle, right? So as you iterate, what you do is you use this code to uh, find out like where the points are located. So if you what you do is, like in the code that is given, you keep first execute this part of the code, then you execute this part of the code, then once more you execute this part of the code and check this part of the code. What you will be able to see is like you'll be able to see the particles that are there in the screen. They move towards the minimal region, right? So they will try to converge towards this region. That is what you'll be seeing in the rest of the code, right? So this also, like, you can have a very good visualization of like how the particle swarm optimization really works, right? So this is another code. So one more code is the so so this is the fourth code. So one thing that you can see is like in Jeeks for Jeeks, like there are several other heuristics that are present. So you can check out this particular site to maybe and along with their implementations have also been given there, right? So you can check this particular site to maybe get more information. Say something like whale optimization, so dragonfly optimization, and so on, right? So several other uh, information along with their implementation details. I mean, some toy code are given, like, which you can uh, try, right? So all of these work very well with Google Colab, and so it means that you don't have to exactly install anything. So, so with a Gmail account, like, you'll be able to run these programs. So here, like, what we see is that there are two functions. So the two functions are called as rastrigin function and sphere function. Sphere we already saw. So rastrigin function, it's basically a non-convex function, so it means that it's going to have a region like this, right? So a convex function has a plot like this. So it's basically a sphere is a convex function. So rastrigin function is a non-convex function, and it is often used or it's used as a performance test for optimization algorithms, right? So now you may have a function with maybe two or more variables, and because of this complex non-convexity, what may happen is, like, here this may be the global minima, but then there is always a chance that the solution region given is this particular trough, right? So the it actually, like, so rastrigin function is basically used as a function to check the optimization algorithms, right? So it sort of benchmarks the optimization algorithms to see, like, if the optimization algorithms are able to find out this global minima or not, right? So you have this rastrigin function, and rest of the functions that are given are similar. So you have a particle. So the particle has over here, like we also have a thing called as a seed. So you have a position and you have a velocity, you have a best particle position, and you have fitness, right? So all these variables are there, like which you have you initialize. Then you have this PSO, in which like you have these three constants that are initialized. Then you iterate in the PSO algorithm for every particle. It's find out its velocity and the current position, so that you after say that many number of steps, you end up having the best swarm position, right? So this is one another algorithm, which I mean, this is the same PSO algorithm with not much variations, like which also you can try. So in this Geek for Geeks, like what they've done is they have used this rasterization function as a function that is used across various um, um, various optimization algorithms, and they have checked both this rasterization as well as the sphere function, right? So this code also, like you can check out. So do you have the have you received the code?
Yes, sir. We shared the links.
Okay, all of you, like would you like some
We
time
shared
to
it in the WhatsApp group and also in the chat box, sir.
I had shared it to that Lavanya madam.
Yes, yes, sir. Forwarded, sir,
Okay, okay,
in the WhatsApp group and also in the chat
okay,
box.
okay. So there are several functions, like which also you can try in order to check these programs, right? Say because these are naive programs, so they may not work well for every function. So rasterization is one function. So rasterization function. So then, as we already saw, sphere function. Then we have something called as Ackley function, right? So this is a function of two variables, right? So f of x and y. So this you can check, or like there is a function of one variable called as the Rosenbrock function. Right? So these are some of the functions like which you can check as functions for optimization, right? So um, there is a function called as Himmel-Blaus function, right? So this function is a function of two variables, x and y, and this is given by x square plus y minus 11 the whole square plus x plus y square minus 7 the whole square. So what you can do is you can use this function, and if you take here, So over here, like you can replace in its position. Uh, Here over here, like you can replace over here maybe the Himalblaus function, because this is also a function of two variables x and y, and check like how the Himalblaus function works with respect to this. Similarly, like what you can do is you can change the number of particles, you can change these constants, right? So we have these three constants that are given, right? So you can change the constant of the social and the cognitive coefficient, and see like how you are able to get to the solution, right? So whether like you are able to get to the solution or not, you can check with respect to the various problems, right? So these three functions, right? C1, C2, and W. This also you can vary in order to see like what solutions that you get, right? So now we'll go to the next thing. So so there is another meta heuristic that is called as Gray Wolf optimizer, right? So this is also a population-based meta-heuristic algorithm that simulates the leadership hierarchy and hunting mechanism of gray wolves, and basically uh, it tries to simulate this, and it is able to produce some uh, results, right? So now so what we can see is that like there are these gray wolves are considered as the top predators, or like they are and they prefer to live in packs, right? So basically like in all the meta heuristics, what they do is they have a they have a overall, or like they have a nature behavior, and they convert this natural behavior of some organism into some mathematical model, right? So they have some equations, or like this natural behavior is organized into some interaction between some steps, right? So you have a step 1 and you have step 2 and you have step 3, and now the interaction between these different steps are put are converted into some mathematical functions, and then like you basically have a mathematical model for this behavior, and then like they alter the solutions based on this mathematical model to get more refined solutions, right? So now every time they get more refined solutions, they check these more refined solutions for fitness, and as the best fit solutions are taken, and then rest are thrown away, and that way like iterations are carried out, right? So here like what we see is something called as a gray wolf, and gray wolf is maybe it works in group, and it consists of say 5 to 12 members, right? So in one group, right? So now the members in a single group, they have a hierarchy, right? And this hierarchy is what is given by say something called as alpha wolves at the first level, and then you have the beta wolf, and then you have delta wolf, and you have gamma wolf, right? So 1, 2, 3, and 4, right? So you have basically these four types of wolves, and these alpha wolves are the ones who take the major decisions, or like they are the ones who take the decisions, and what are the decisions that they have to take, whether to hunt or not, right? So those decisions are taken by these um, alpha wolves, and rest of all the members, they have to acknowledge the alpha wolves decisions, right? So they have to abide by the alpha wolves decisions. So now the second type of wolves are the beta wolves, and the beta wolves can be, I mean, so maybe the alpha wolves are uh, uh, they are they are actually like they are a male and a female. And here in the beta worlds, like there can be multiple males or females, and these will be the best candidates if the alpha wolves pass away, right? So if the alpha wolves pass away, then these beta wolves are the best candidates to become the alpha wolves, or if alpha wolves are very old, then these beta wolves are the best candidates to become the alpha wolves, right? So now they sort of also give feedback to the alpha wolves, right? So now that is their function. Now you have the delta wolves, and these delta wolves are not the alpha or beta wolves, and they are subordinate wolves, and but then these delta wolves dominate the gamma wolves, right? So or these are um, uh, omega wolves, right? So you have omega wolves. So these delta wolves dominate the omega wolves, right? So now there are many categories of the delta wolves. Say some like scout wolves and so on, right? So there are many categories of the delta wolves, right? So now the one is scout wolves, then you have something called the sentinels, then you have something called as elders, then hunters, and say caretakers, right? So these different types of delta worlds are present, and these omega worlds, these are the final set, and they are basically the ones who are the work horses, right? Or like they have to just obey whatever the rest of the, or importantly the delta worlds, and they are the bottom in the entire hierarchy, right? So bottom in the hierarchy. Right? So they are not so important. And if there is a hunt, then according to this hierarchy, the alpha, beta, and gamma eat, and finally only this alpha, omega wolves will be able to uh, come, right? So now so in the normal setting, like the, so basically you have the solutions. So solutions are basically the wolves, and now the solutions, like you have the fittest solution as the, so you have fittest, then second fittest, then you have third fittest, and then rest, right? So the fittest is called alpha, and the second fittest is called as the beta, and the third fittest is the delta, and the rest are called the omega, right? And here, like in the GW algorithm, so you have different phases. So now the hunting phase, in the hunting phase, hunting is basically guided by the alpha wolves, right? So or like alpha solution, right? So the hunting is guided by the alpha solution, and the omega will just follow the alpha solution. So during hunting, like what they do is like the alpha, the gray wolves, like the wolves, basically they encircle the prey, right? So this is a normal behavior. So now this encircling of the prey is given by the following equations, which is given by d equal to c into xp of t minus a into x of t, right? So this encircling of the prey is given by these two equations. Right. So these two equations, they sort of give the encircling of the prey, and here like t is the current iteration, and a and c are the coefficient vectors, and xp is the position vector of the prey, right? And x is the position vector of the gray wolf, right? And we also have this a and c that are computed as a equal to 2a into r1 into a, and c equal to 2 into r2, right? So where this a is a component that is linearly decreased from, so it means that in the initial iteration, like it is 2, and then in the later iterations it is linearly decreased from 2 to 0, right? So a will be ranging from 2 to 0 over the course of iterations, and you have R1 and R2 as the random uh, uh, vectors in 0 and 1. So you have some random vectors which are given by given between 0 and 1, right? So now, so basically like you have this encircling the prey that is given by these equations. So now this, as I already told you, like the alpha wolf is going to guide the hunting operation, and now beta and gamma may occasionally participate in the hunting, right? So basically, like what we mean to say here is that, say you have a solution like which is the fittest, so this solution basically determines like how the further solutions are to be refined, and rest of all the solutions, like all the possible solutions, they follow this optimal or like near optimal solution. Then like sometimes like the second best optimal solution may also determine like the best solution, right? So but in general, right, it is assumed that the alpha has better knowledge about the location of the prey, right? So now that is what happens, and the updation of the rest of the positions, rest of the agent positions, that is done according to this formula that is given as d alpha equal to c1 into xa minus x, d beta equal to c2 into x beta minus x, and uh, uh, the delta equal to c3 into x delta minus x, right? So x alpha, x beta, x delta, right? So you have these d alphas. Then similarly, like you have the positions x1 equal to x alpha minus a1 into d alpha, x2 equal to x beta minus a2 into d beta, x3 equal to x delta minus a3 into d delta, right? And xt plus 1 is given by x1 plus x2 plus x3 divided by 3. So now this is how like the hunting and the updation of the positions of these wolves take place. And the gray wolf, it when the prey stops moving, then the gray wolf attacks, right? So now that is what happens. So basically, like we see the vector A, right? So A is a vector which is in the random value, which is a random variable value in the interval, which is minus 2a comma 2a, right? So we know that a is a variable that decreases from 2 to 0 over the course of the iteration. So we have capital A as a value that is between minus 2a and 2a, right? So now when, so it means this is a random value. So when a is, when mod of a, when a is less than less than 1, so when mod of a is less than 1, then the wolves attack towards the prey. So it means that like that is, this sort of shows the exploitation. Otherwise, like if the value of this a happens to be more than 1, it denotes exploration, right? So if you look at the iterations, say if there are 50 iterations, then we see that small a will be ranging from 2 to 0. And as the value of a becomes less than 1, then the chances of exploitation becomes more, right? So the chances of exploitation becomes more, and maybe until then, like, the chances of exploration becomes more. So it means that there is a balance that happens between the exploration process and the exploitation process, right? So now when mod a greater than 1, then what happens is the wolves do not attack, or like they do not uh, attack, and so there is a thing of divergence, right? So they diverge from the prey to find more fitter prey. So it means during the initial iterations of the problem, so what happens is, like, they try to diverge, and they try to find out better prey, and then, like, as they find out few solutions, like they try to attack the most fit of the prey and try to uh, get to the final solution. So this sort of gives the overall view of the gray wolf optimization problem. So, or gray wolf optimization procedure, right? So what we do is, if you look at the overall algorithm, so in the step, in the initial step, like what you do is we set the initial values of the population size. So we have initialization. So in the initialization, like, you basically set the population size. The population size is set as something, and then you have the parameter a. Then you have the coefficient vector a and c, and you also have the maximum number of iterations. So max iterations. So then we have maybe, like, we have the time t equal to 0. Then what you do is, like, say you generate the population, right? So this is not time, say, for t equal to t up till n. N is the population size. So what you do is generate the initial population xi of t, right? So this is generated randomly, and now you also evaluate the fitness function of each of the agent, right? So using maybe a function f, and you try to find out what is f of xi, right? Then so it means this is the initialization step, and this is quite similar to, like, our PSO algorithm, right? Then what you do is you based upon, like, the fitness values, what you do is you assign the first, second, and the third best solution to x alpha, x beta, and x delta, right? So these are assigned the alpha, beta, and delta respectively. So then you have to repeat, right? So repeat so until maximum iteration. So what you need to do is for each of the wolves. So what you do is like uh, we update the um, uh, parameters. So we find out the behavior of the parameters as it was said with respect to D and X, right? So D and X. Similarly, like we also find out this D and X T plus 1, right? So now you find the D and X T plus 1, then you decrease the uh, parameters, parameter A, right? So because we know 0 to 2 and we have to divide it by maximum number of iterations, and stepwise like we have to decrease it, then update the coefficients A and C, and then like compute the fitness function f of xi, right? So then once you compute the fitness function, then you end this for loop, and then what you do is you find x alpha, x beta, and x delta. So it means every for each of the workers you compute the fitness function, and then you update x alpha, x beta, and x delta, and then once more like you go along that particular direction, right? So this is what you need to repeat for each maximum number of iterations, and for maximum number of wolves. Then you keep repeating this, and then like finally you find the best solution x alpha, right? So this is going to be your best solution, right? So this is what is given with respect to the Grey Wolf optimization, right? So this is once more like given in your, I mean, I think I've shared the code for this one also. So I'll just get to the code.
ஹலோ அங்கிள் என்ன பண்ணிட்டு இருக்கீங்க? அப்படியா? ஓ இன்னைக்கு வந்திருக்கா? அப்படியா? அப்ப போறீங்க இப்ப போட?
I request the participants please mute yourself.
So here, we once more see this Grey-Wolf optimization that has been applied with respect to the same two functions, like Rastrigian function as well as the sphere function. So now, just as in the previous case, we could see that we have some initial positions that have been initialized with, and then you have the fitness that is found out with respect to the different positions, right? So now we have the Grey-Wolf optimization. So here too, you have a population of n random wolves that have been created, and then then the fitness of each of these are computed, and then the fitness is uh, mm, uh, sorted, right? So based upon the sorted fitness values, you assign the top three of the population to alpha wolf, beta wolf, and gamma wolf. Then we come into the maximum iteration. So for maximum number of iterations, as we saw earlier, you find out the variables which are a1, a2, a3, c1, c2, c3, and then you also find out the positions, and then you update the positions using this a and c variables, and then you have these positions that are done, and then you find out, so basically, what in every step what is being done is, then you have this x1 that is computed using this alpha wolf position, then x2 that is computed using this beta wolf position, say x3 is computed using this gamma wolf position, and then based on that you find out the new position for this particular wolf, right? So it means that these three wolves determine how the rest of the members of the group, they have to move with respect to the solution, right? So now once more, after doing this, you divide it by 3 to find out the new position. Then you do the fitness, calculate the fitness for this particular new position, and then you check if the new position is to be taken or not, based on if the fitness is good or bad, and then once more you sort the entire set of fitnesses and assign the top three fitnesses once more to the alpha wolf, beta wolf, and gamma wolf, and you keep repeating these three things, these steps for the maximum number of iterations to finally get the alpha wolf position, which is going to be a solution, right? So this is the procedure that is followed with respect to this Grey-Wolf optimization. And with respect to most of the optimization problems, these are the steps that are followed. The steps are that you have a nature inspired behavior, and this behavior is converted into some mathematical function, and then based on this particular mathematical function, you have a set of steps, and these steps are repeated over and over on some initial solutions to obtain the final solution, right? So these are the things that are followed in order to get the solution. So if you have any queries, like we can discuss. So anyhow, like so far I have never received any queries. So what's the type of audience? Like are you all researchers? Are they allowed to talk? I mean, so are you all researchers or what you're doing?
Sir, research scholars are there, administrators, and the academicians. Everybody is there, sir.
Okay.
They are allowed to talk, sir.
Yeah, yeah, yeah. Yeah. Anything you want to ask me? You
Sir,
can. Yeah. Yeah. Please.
is the discussion is over, sir?
Yeah, I think they have to say this people, the audience
Okay,
have to
sir.
say. Yeah.
Okay, okay. So I request the participants, if you want to have any questions, requested all of you, please.
Excuse me, sir.
Yeah, yeah, please.
Sir, this fitness function is the classifier independent.
Is the fitness function classifier independent? So I did not get the question. So what do you mean by that? So how do you put the classifier and the uh, fitness function together? So here, like say, so basically, like this is that you have a function which you want which you want to optimize, right? So this is a function of x and y, and this function you want to optimize, right? So you want to find out the what do you mean by optimizing this function? It means that I want to find out that value of x and y for which f is either minimum or maximum, right? So now this function itself can act as a fitness function, right? Say for instance you have a big room, okay? Now this is a room of say 3000 square feet. Now you enter into the room and you have a gold coin, and you were roaming here all around the room. Somewhere you lost the gold coin. Now what is the approach that you will, what approach will you follow to take back the gold coin? What is the approach that you will follow? One
We'll
is,
search it.
yeah, I
We'll,
have
we'll do
to,
search. We'll do search.
yeah, you have to do all around the length and breadth of the room. I can do a search. But let us assume like you have only half an hour. You have to catch a train to go somewhere, or like you have a flight which you have to catch. Then what will you do? Right? So what you can do is like, okay, you if you recall like where you exactly went, right? Okay, I did not go to this corner, I did not go to this corner, I did not go to this corner. This entire place I did not go. If you know that, then what you'll be doing, you will be restricting your search to some specific region only, right? So now the problem is exactly like that. Okay, so can we reduce our search space so that we don't have to search everywhere, but rather like we will have to search only in some specific region? Say for instance, if you know the value of x and y to be between -10 and plus 10. So x can also take values between 10 and minus 10, and y can also take values between minus 10 and 10. Then the search space is going to be, say, minus 10 to 10 and minus 10 to 10, and this entire space is infinite space, right? I cannot search this entire space. It is going to take maybe years and years to find out the optimal solution. Is there a shortcut, right? Rather, if there is a shortcut and if I can arrive at that shortcut very quickly, then I want that kind of a solution. So that solution is what is given by these meta-heuristic algorithms. Now, when I do this solution, I need to use a fitness function. So what is my choice of fitness function? So here, like, the optimization objective itself can be used as a choice of my fitness function, right? So the optimization objective is maybe to optimize, as I told you, x0 square plus x1 square, right? So find out the minimum x of 0 and x of 1 such that this is minimized, right? So the optimization objective function is this one. So the value of this one for some x of 0 and x of 1 is, this is my function. The value of this function for some x of 0 and x of 1 will be my fitness function value, right? So the optimization objective itself can become my, or optimization function itself can become my fitness function. Is that okay? I mean, did I answer?
Yes, sir.
Yeah. So were you able to execute the code? I mean, did you try? Did any of you try?
Sir, I have one doubt, sir.
Yeah.
Sir, how to use that Rastrojin function for feature selection? Can you just elaborate on it?
Rastrojin function
Now,
for
here the code, sir. Somewhere I have seen.
yeah, rastrojin function is not used for feature selection. So see, now if you take a rastrojin function, so this function is basically a non-convex function.
Yes, sir. But sir, I have gone through some papers. They are using this function for feature selections. So how to use it, sir? Can you just elaborate it, sir?
Rastrojin function for
And I was
features.
confused when I read the papers.
Okay. Uh, I have not. I don't have any idea about that. Like
Yes, sir.
how
Sure, sir.
rastrojin function may be useful for feature selection. Yeah.
Fine, sir.
Yeah.
Thank
Yeah.
you.
Sir, namaste.
Yeah. Yeah.
Sir,
Namaste.
just I want to know for beginners, for
Yeah.
begin researchers, those who would like to start their work in these SWAM optimization or maybe rather bio-inspired computing, for them, what are the ways to explore, sir? Maybe what are the places where they contribute? Because if you look at a genetic algorithm or any heuristic algorithm, you have like initializing the population, then finding out the fitness function, or maybe updating it, and again check the fitness, select the best individuals with best fit, then iterate it. This is
Yeah.
almost a general procedure for any these uh, bio-inspired algorithms.
Yeah.
So for beginners particularly, how they can contribute to the researcher, maybe to a PhD thesis or so, where
Yeah.
they can
So
work.
yeah. So I think, like, see, okay. I mean, after getting lots of idea about this bioinspired maybe like with respect to contributing with respect to bioinspired algorithms can be looked at, but initially like there are plenty of scope for applying this bioinspired in various areas itself, say for instance wireless sensor network, right? So now you may want to find out maybe like a traveling salesman problem, or you may want to find out some path, right? So optimal path, right? Or like you may find out some optimal location at which like you need to place the sensor nodes, right? So you have a area, two-dimensional area, and you have a base station over here. And then, like, if the sensor nodes are to be optimally used, then there has to be an optimal topology in which the sensor nodes are to be placed, right? So, what is the optimal topology which is going to be energy efficient? So, there are plenty of problems. Like, if you look at computer networks, then there are research problems like where this novel IoT has come into the picture, sensor networks have come into the picture. So where like you can still apply these algorithms. So what I feel is that instead of initially itself looking at varying the bias-spread algorithms, what you should be looking at is the applications. So where all you can apply, say for instance, these days drones are being used for monitoring the agricultural fields, right? So what should be the optimal maybe topology of the drone, or like how the drone should move optimally in order to minimize their energy requirement?
Okay.
So something like that. I mean, so you look at the application, and then you see like how which because you have plenty of bias-spread algorithms, you try to apply any of these bias-spread algorithms onto these applications. Yeah, then you obviously like you will be able to get some results which you can publish, or like which can be useful. So I suggest you to look at applications.
Okay.
And later on, after getting lots of understanding, then you can look at, okay, so I should vary the bias-spread algorithm.
Okay, sir. Thank you, sir.
Yeah,
So,
thank you.
I
Yeah,
have a question, sir.
yeah.
So, what about the medical domain, sir? Bio-inspired in medical domain.
Yeah, medical domain also like
So, you
bias-spread
can suggest some
algorithms.
applications.
So, with respect to, say, for instance, like one is, if you look at, not many I'm getting, but then say if you look at segmentation, right? So with respect to segmentation, like one of the important thing is, say, you can say region filling, right? So region filling is a method, right? Now, if you use region filling, now finding out the seed point is a important step. Say if you do not find the seed point correctly, then your region filling may not give you optimal segmentation, right? So then like you can use some bias-spread techniques to find out the seed points, right? So this can be one specific application, right? So like this, like you can have plenty of them, say either with respect to this kind of a segmentation, maybe with respect to say removing some of the fuzziness in the segmentation output. So there also like you may find out some applications for bias-paired algorithms.
So, in prediction of any disease or like cancer, like it can be used, sir.
Prediction, okay. Say one another area, say when you say prediction, basically like you talk about machine learning algorithms. So if a machine learning algorithm has some hyperparameter, right? Now with respect to this hyperparameter, you can always use Bayes-Spread algorithms, right? Finding out the hyperparameters in order to use this machine learning for some data set, right? So because once you say prediction, it means that I have to learn, right? I have to learn something in order to predict, right? I have a data, I have to learn something from this data, then I use this learning to predict, right? So that is the idea, right? Now, what if once I say I have to learn, then it means I assume that there is a model that is present here, right? This model is going to have parameters and hyperparameters, right? Now, how do I get the hyperparameters? I have to tune, right? So this is a big task. I cannot tune over a large space in order to get the hyperparameters. Then I can use some Bayes-Spread algorithms for finding out the hyperparameters. Say, for instance, a neural network, right? So number of layers, number of neurons in some specific layer, right? Maybe all of these, like these, you call as hyperparameters. So for this, like you can use some Bayes-Spread algorithm. People use genetic algorithm and so on for these hyperparameters.
Okay, sir. Thank you, sir.
Yeah, thank you.
Sir, regarding tuning the hyperparameters using Bayes-Spread algorithm, let us say genetic algorithm, here the initial population would be the what is that number of layers? Let's say if you look at the number of layers, let's say I'll start with one hidden layer, two hidden layers, three, like that. We need to take and work on.
Yeah, see, the thing is like the idea is like this. If when we are tuning, like we cannot go for a complete search space, right? Because it's going to take a long amount of time.
Yeah, correct.
So it means that like you have some way in which like you say that like I will not go for entire search space, but then I will use only these hyperparameters which are used by a genetic algorithm to get the answers, something like that, right? So that way, like you can do instead of going for a complete search.
Okay. But for genetic algorithm, if we use, even let us take one example like number of layers or maybe number of neurons in each layer, I want to find out optimally. Then I need to set a initial population, right?
Yeah.
So in the initial population, those are like candidate solutions.
Yeah.
Maybe let us say number of layers I want to decide optimally.
Yeah.
So initial candidates could be like I can give one candidate could be one layer, one, maybe another can be three, like that. Randomly, we need to pick within some range, right? That's an idea.
Yeah, so randomly we need to pick the range, but then see there are obviously challenges. Like say the
Yeah.
challenges will be what will be the fitness function here,
Yeah,
right?
that is a
So
challenge. Yeah.
yeah, so the fitness function, like say if you're going to say for instance like 100 you get a solution, 200 you get another solution, then like maybe for these two values you will have to have a fitness function, get some fitness values, and based on these, like if you are able to do some kind of crossover mutation and then find out some solutions like which are given by your genetic algorithm, then you use it on your thing and say that okay, I used 100, it was not giving good results, but it was over in less time. I gave 200, it gave very good results, but it took a huge amount of time. But then like instead of 150, 180 was the right amount of thing which was provided by algorithm, and So what is the idea here? I am not using 101, 102, 103. All these intermediate values I am not using. I am just using a genetic algorithm which I gave some population. It gave me 180. Then I put it here and I got some results which were near optimal. So I am happy. Something like that.
Yeah, correct. Yeah. So designing maybe objective function is a challenge, particularly.
Yeah, fitness function here with
Yeah.
respect to this will be a challenge. Yeah.
Okay, sir. Thank you, sir.
Yeah, thank you. Okay, I think I shall.
Participants, any more questions?
Sir, good morning, sir. This side
Yeah,
Sonu
yeah,
here. Sir,
yeah.
suppose I will work on based on some large amount of data, like deep data set for some biometric sensors based research. So how we can process these type of data? Because till now I have means implemented with only one file, with like one .csv file. So if I will have multiple channel type of data set, then how we can perform, sir? Uh, Sir, are you getting my point, sir? What I want to ask, sir?
Yeah, what you're asking is like if there is huge amount of data, then how do we process it? Is that you are asking, right?
Yes, sir. Yes, sir. Yes, sir. Multiple
Yeah.
file we are having, and we will process. So, like three channel or 3D CNN. What type of technique we will use, sir?
What's the application? Like what application are you working on?
Sir, I'm working on some emotion recognition type of.
Okay, in for emotion recognition, like what kind of data you
Data,
have?
sir. I'm having deep data set, sir.
Say you have because yeah. No, no. See, emotions can be say if you are going to predict an emotion.
Yes, sir.
Now I can have a text data and I can predict the emotion.
Hmm.
Like if I watch this movie, like what is the emotion? I can have a book
Yes, sir. Yes.
summary and I can predict the emotion. What is exactly the data that you have? Whether you are using one file or multiple files is not
Yes,
the
sir.
question.
Multiple file I'm using, sir. Like
नहीं नहीं
I'm.
वो क्वेश्चन ही नहीं है. That is not the way of saying a problem. So
Uh,
file
okay.
में क्या है? Like eventually like you're not going to process on the files. You're going to process it in the memory. So whatever data that is there, like you're going to take it into memory and have it in some variable, and then you're going to process it. So फाइल का क्वेश्चन नहीं आ रहा है. Say for instance, what is emotion recognition? Is it a classification problem?
Yes, sir.
Okay, if it's a classification problem, now what are the input variables? How many input variables do you have?
Sir, input variables means for yeah. Suppose I have given some. I have collected some video type of data as well, sir. So suppose
Okay.
and based on that, I have collected happiness, sadness, or neutral type of data. So suppose we are having some different type of electrodes, or and we have collected data from different electrodes. Then definitely we will have some large amount of files, like more than one files. For example, one channel is having some different file, another channel is having some different types of files. So this is actually the format of deep data sets, sir. So
Okay, I think what you're talking about is using, say, some electrodes and taking the
yes, sir. Yes,
signals
sir.
from the brain or head, and then like you're going to process those signals.
Yes,
So
sir. Yes, sir.
accessing those files is not a problem. You can always read multiple files, put it into memory, and you can process it. That is not an issue.
Suppose, sir, I want to insert some folder type of data, like 2D data. I am working perfectly, sir. Huh? But
Okay.
if I will, I want to give some yeah, folder type of data. Means folder means, sir, multiple files collected in one application, sir. So I'm little bit facing some problem in that. That's why I thought that case, if I will get some
नहीं
update.
इसमें क्या problem है? Like you can use the fopen and you can open the. You use which language are you working on?
Sir, CNN I'm using, sir. Python, sir.
Python. So Python में file access करने में क्या problem है? Like you can always access a file.
Sir,
You can
yes.
always access multiple files. I work on say thousands of files. Like I work on image data set. So उसमें तो like हर image के लिए like around 200-300 files आते हैं और 1000 image आ गया तो like I will have more than 1 lakh file.
Okay. आई थिंक मैं एक बार सर ट्राई फिर से करता हूँ उसको। मैं 3 डायमेंशन में देख रहा था थोड़ा सा, तो इससे मुझे लगा जो सर इससे शायद कुछ क्लियर। मैं आपका वीडियो फिर मैं देखूंगा तो शायद कुछ क्लियर हो पाएगा सर इससे।
फाइल रीडिंग उसमें तो दैट शुड नॉट, बिकॉज़ दोस आर ऑल नॉट टेक्निक रिलेटेड। वो तो लाइक इट्स अ एलिमेंटरी थिंग ओनली। उसमें इतना प्रॉब्लम नहीं होना चाहिए।
मैं देखता हूँ सर फिर एक बार।
ठीक है,
आई विल ट्राई डेफिनेटली सर। ओके सर, थैंक यू।
ठीक है, प्लीज। हाँ, ओके।
Participants, any more questions? Okay, sir. Thank you for your wonderful talk, sir. This helped us a lot to move forward in our research and career, sir. Thank you very much, sir.
Yeah, thank you very much. Thank you for the wonderful opportunity. So, and thank you for all the questions that you are all asking. So, thank you. You can also reach me at godfrey@AAATM.ac.in. So,
Sure, sir. Thank you, sir.
Yeah. Okay, thank you.
Thank you for support, sir. Thank you.
Thank you.
Thank you, sir.
All the participants, please take the break for 10 minutes and we will join back again at 11:40. Thank you.